Welcome everyone to the informational webinar on IPAM's Spring 2026 long program on multi-fidelity methods for fusion energy. We're holding this Zoom call to inform you all of the format of an IPAM long program and what you can expect as a long-term core participant or a participant in a workshop of the program. And also to provide you an opportunity to hear from the organizers who will be here during the program as well, and will give you an overview of these program scientific focus. And we'll also go over the scientific focus of each individual workshop. The order of this session is the following. I will go over a couple of slides to inform you all about IPAM and our mission. And then the organizers will discuss the overview of the program and the workshops within the program. And I'll end with information about the general format and what you can expect during the long program. Before we begin with all that, let's go over a bit about IPAM and our mission. So IPAM is an NSF-funded mathematical sciences research institute, and we're housed on the beautiful campus of UCLA. Our tagline is "Math changes everything." It is our mission to bring together researchers in mathematics and other disciplines like physics, chemistry, material science, and so on, to build new interdisciplinary research communities. And part of the way that we do this is through long programs, so these 14-week long programs, like the one that you're here to learn more about now. We build these new communities, give them the space to do so. So IPAM has its own building, as I mentioned, on the UCLA campus. For the long program, you would have your own office if you're here. Excuse me, not your own office, but you'll have office space. Some of those shared here in the IPAM building. And we also, of course, contribute to the workforce development of the mathematical sciences. Part of this is by highlighting mathematics as a viable career path, making sure that people know that this is a driving force for innovation, and really to engage and transform the world through mathematics. So again, math changes everything. So while you're here at IPAM, you will be helped with our great IT team, finance, program staff, and we also have a chief administrative officer. Our goal is to make sure that all of our staff and the scientific directorate help out so that you don't have to worry much about the logistics of being here, of hosting these programs. Really, all you have to do is worry about the science itself. The scientific leadership is responsible for planning and executing all of the scientific activities here. So we have Dima Shatenko, who's the director. Christian Roche is the deputy director. I am the associate director, Selenne Bañuelos. And our director of special projects joining us this academic year is Terry Tao. Perfect. So how does IPAM fulfill its mission? As I mentioned before, we have these 3-month-long programs. Within them, they have built-in workshops. We begin with a tutorials week and end with a culminating retreat. And I'll discuss more about those details towards the end. We also have standalone workshops as well during the winter. So these are not necessarily associated to a given long program, but they can just be their own workshops, week-long workshops. We also have summer schools or winter schools, industry short courses. We actually have one coming up this winter. And over the summer, we also engage in undergraduate and graduate research opportunities. So we have the RIPS program that runs here in Los Angeles, and we also have partners with Sandia and Berlin for the graduate RIPS program. These are really great. They give students the opportunity to work on a research project that is actually coming from industry. So it's a nice blend of having just an REU experience, but also in the industry setting. So this gives you an idea that we are a year long. We do have programs year round. So long programs start in September and in about December, and then March through June, and workshops in the winter, and summer is busy with the RIPS program and other summer opportunities. But also I am including this diagram below to show you all that, yes, we are a mathematical sciences research institute, but again, mathematical sciences and how it feeds in and how it helps promote other disciplines as well and advance those disciplines as well. So as you can see from here, we have people from physical sciences, engineering, computer science, and all that as part of our programs. So this gives you the pie chart of the different disciplines that visit IPAM. And of course, we have quite a few people who are trained mathematicians in physics departments and engineers and so on. So it's all kind of, we're all in the same boat here. So again, today we're here to talk about the long program on multi-fidelity methods for fusion energy, beginning March 9th through June 12th, 2026. So with that, I will stop sharing my screen now, and I think Frank is going to begin sharing his.
So this is what our long program is called, and on the right you see again the list of main organizers. And as you all know, in December of 2022, we had this major event where for the first time we got more energy out than was provided, in this case in inertial confinement fusion. They have since then improved this performance from a factor of 1.5 to a factor of about 4. And at the same time, on the magnetic confinement side, we've had successes with a jet, for instance, providing, I think it was 69 megajoule of fusion energy out. And we had world records set by W7X, this big stellarator. And many other good things happened. And we see a lot also happening on the startup scene. So all of these things are very, very interesting and very promising. And this is an idea that Jeff introduced, kind of where we are in fusion. And he likes to compare it to the Wright brothers' moment in the development of human flight. And you could say that we're just starting to get serious about fusion energy. Basic research, of course, has been around for many years, but now we are focusing as a community throughout the world more on the energy goal. And computation and theory and math can contribute a lot to this goal, because, as I like to say, in the old days, when experiments were small and cheap and fast to build, you could just try out ideas in the lab. You could just say, okay, why don't we build an experiment that does this and that? But now that experiments sometimes cost billions and take decades to design and build and analyze, if you want to get to the goal within reasonable time periods, you need to go faster. And this is where math and computation can kick in and help a lot. But there are some challenges. Like in many other areas of science, you have multi-scale problems. The spatial and temporal scales vary by many orders of magnitude. You have, in many cases, complex multi-physics issues where different types of physical processes interact with each other in interesting ways. And you cannot simply use superposition principles to disentangle the complexity, but everything hangs together in some weird way. Often these interactions are strongly nonlinear, and this means there's even more cross-scale coupling and things like this. And it's very difficult sometimes to come up with a really reliable description of the underlying processes. So there's really a lot to do on the inertial fusion side. We need to implement more efficient drivers. We need to have much more cost-effective targets. The repetition rate needs to be increased from a few times a day to at least 10 times a second. On the magnetic side, magnetic fusion, we need much longer discharges. Currently, we are approaching 20 minutes or so, but we need much longer, or a stellarator. And we need to optimize many configurations, take care in both scenarios, magnetic and inertial, about plasma-facing components. So materials development is very important. You have to try to come up with something like a digital twin, maybe, so that you can design, model, optimize, improve entire systems. You need to have a real-time control in place. And then there's the whole issue of waste removal, recycling, safety, and many other things. So there's a lot of problems still to tackle. And in all of these, I would argue, again, math and computation can be very important contributors. Obviously, once fusion energy will be commercialized, this will have a transformative effect on our societies and economies. And we really can use this long program to spark some new activities and new ideas. This is, of course, always it's always a big opportunity if different disciplines join forces, because this provides opportunities for new things to happen. Often they are not planned, but they happen if you bring together the right people with the right skills and the right attitudes. And Jeff and I have been part of a long program back in 2018 where exactly this happened. And personally, I have benefited up to this day, so the last 7 years or so, from some of the ideas that were developed in the context of this long program. And I hope the same will happen again in this case, such that we may break maybe also the conventional wisdom that fusion is always 20, 30 years away or something. I think, again, computation, math can contribute to nailing this one down in all of its different aspects. So we will be physicists, mathematicians, computer scientists, engineers, and maybe others coming together for weeks or months, depending on people's availability. And we will have an opportunity to discuss our different ideas, our methodologies, our simulation approaches, and we can build on what we have developed in the past and try to come up with brand new ideas, and hopefully also have some breakthroughs and significant developments. So the key buzzword in this context is multi-fidelity. I think everyone is aware of high and low fidelity models, and they exist in all areas of science and engineering, but very often they are used independently. And what we want to discuss in particular in the context of this long program is ways to combine high, mid, low fidelity models in a very dynamic way, such you can get the reliability, predictability of high fidelity models together with the speed and the efficiency of low fidelity models in an integrated way, so you can do scoping studies and optimization and uncertainty quantification and similar things. You need a lot of throughput, and you can combine this with high fidelity models such that they work together in a very interesting way. So some of the questions we want to address is how can we use a hierarchy of models to accelerate simulations? Again, we want to use the best of any level of fidelity of the models that we use, as I just indicated. And examples would, for instance, include that we have first principles models. I mean, in fusion and magnetic fusion, gyrokinetics is perceived as such an approach. Sometimes it may be 6D kinetics. And then there are reduced versions. There's fluid theories. There's reduced kinetic theories. You could get rid of certain scales, and you could reduce the resolution. You could do all kinds of simplifications to go to mid and low fidelity models. These days, people are also using machine learning more and more to come up with reduced models, which sometimes are even real-time capable. And again, you want to do things like sensitivity analysis, uncertainty quantification, optimization, where you need really fast models so that you can evaluate maybe millions, billions of times if needed. So all of this comes together in this long program, and here is an overview. This is the last slide. This is an overview of our main activities in the sense of the really active weeks where we have workshops or tutorials. Of course, I think the entire program is, if I'm not mistaken, 16 weeks or so. And here's 5 weeks, and there's a 6 week, which is the culminating workshop at Lake Arrowhead. So the 6 weeks are booked out by these workshops and other events. And the weeks in between are also meant to be very active, but in a very different way, in the sense that, we share our offices, we are next door, we talk to each other, we have seminar talks, we can work on all kinds of things, and we can further develop the ideas that are developed during these events. And I will not go into much more detail because we'll have separate reports, if I understand correctly, from the leaders and organizers of these workshops. But they hang together in a certain way, but they also try to look at the elephant from 4 different directions, which all, completes together our view on this interesting topic.
Great. Thank you. Thank you very much for that introduction. And Jeff, again, feel free to chime in at any point during the call as well. So here, as Frank was mentioning, we have events programmed during it's a 14-week program. And the opening day is on March 9th, 2026, followed by 4 days of tutorials. And then we have these 4 workshops planned scattered throughout the long program with off workshops in between. So I'll talk more about the tutorials and the culminating retreat in a couple of minutes. But first, let's begin with describing the first workshop. And Emily, it's your turn.
Hey. Hi, I'm Emily Belli, and I'm one of the organizers of Workshop 1, along with Hans-Joachim Bungartz, Frank Jenko, and Elizabeth Chen. And this workshop is called Multi-Fidelity Methods for Fusion Plasma Physics. And the overall scientific scope, building on what Frank said, is to bring together researchers and form new cross-disciplinary communities to explore innovations in multi-fidelity methods that can essentially bridge the gap between expensive high-fidelity models and reduced accuracy low-fidelity models. And we additionally aim to identify both existing and new challenge areas of research in fusion plasma physics that can benefit from these methods. So for background, in considering concepts for fusion energy, whether based on magnetic confinement devices or inertial confinement devices, both approaches are subject to complex physical processes at a wide range of spatial and temporal scales that directly can affect the plasma stability, transport, confinement, and ultimately the fusion performance. For example, in MFE, instabilities at microscales on the order of the ion or electron gyroradius can induce turbulent transport, such as shown in the picture here, which can degrade the particle and energy confinement and set fundamental limits on operating regimes and plasma performance. And this is often described by kinetic theory, such as 5D gyrokinetics. On the other hand, instabilities at macroscales or system-wide scales, which are often described by MHD, can severely disrupt the plasma's confinement and stability, for example, leading to off-normal events such as disruptions and runaway electron phenomenon that have the potential to damage reactor components and can set severe design constraints. In MFE, microscopic instabilities at the boundary between the fuel and the outer shell of the fuel pellets can degrade the fusion reaction, leading to macroscopic symmetry losses, mixing, and cooling of the plasma. So traditionally, the physics, whether in MFE or IFE, has been studied with focused efforts addressing specific phenomenon, such as microturbulence, energetic particle dynamics for fusion alphas, materials for the walls, or MHD events, with limited coupling and integration. But it is increasingly becoming known that these phenomenon are interconnected in significant ways, often through complex cross-scale nonlinear interactions between the different processes. So first principles models enabled by exascale computing very recently are continuously being developed, but are still prohibitively computationally expensive for most applications. One example is so-called full-F kinetic models in MFE for edge physics that can compute transport spanning both the closed and open field line regions. Reduced models, on the other hand, such as based on semi-analytic approximations, quasi-linear estimations, or fluid models, have become an essential approach for interpreting existing experiments and guiding the design of new experiments and reactors, despite their sometimes limitations and inconsistencies. So advances in multi-fidelity methods that can combine these high fidelity but sparse data with the low fidelity but abundant data from our reduced models are promising to provide an exciting solution. So this is the scientific focus of our workshop. And some of the topics that we will explore include numerical analysis and multidimensional PDEs, non-deterministic methods that can incorporate uncertainties and probabilistic elements such as Gaussian process regression, moving beyond simplified moment-based descriptions for our models and estimating things like correlations. So overall, our workshop will bring together our experts and international leaders with a diverse set of specialized skills, such as theoretical and computational plasma physics, and areas like kinetic theory, MHD, and fluid modeling, as well as computational and applied mathematics in areas like numerical analysis, multi-fidelity modeling, integrated frameworks, surrogate modeling, and uncertainty quantification. So overall, in this workshop, we'll aim to explore adaptation and effective incorporation of these multi-fidelity methods that can combine the speed of our simpler reduced models with accuracy and comprehensiveness of our high-fidelity simulations to uncover some of the challenges and assess limitations and to identify specific applications within fusion plasma physics, such as design optimization, real-time control, and other areas that have previously been unexplored due to seemingly intractability that can benefit from these advances and new innovations in these methods. So, thank you.
Thank you, Emily.
All right. Hello, everyone. And for those of you who joined a bit later on, my name is Ionut-Farcas, and I'm the representative of the team for the second workshop of this long program. So the second workshop builds on the first and is called Learning Models from Data for Multi-Fidelity Fusion Plasma Physics. And I'm speaking on behalf of the organizing team, which is a multidisciplinary team composed of Anima Adamkumar from Caltech, myself, Greg Hammett from Princeton Plasma Physics Lab, Ben Pesdorfer from the Grant Institute at the New York University, and Yunan Yang from Cornell University. And one of the big themes in multi-fidelity modeling and multi-fidelity methods, as the name suggests, is the idea that we have a multi-fidelity set of models, sometimes organized in a hierarchy, from high-fidelity models, usually based on first principles, but that are computationally very expensive to simulate, down to models based on simple algebraic expressions and so on. And in this workshop, we will explore the idea of how we can incorporate effectively models learned from data into multi-fidelity frameworks that are useful for fusion plasma physics. And as we know, as advancements in data-driven learning, especially fueled by machine learning, artificial intelligence, and so on, are present pretty much everywhere nowadays, including fusion plasma physics. It's not always clear how to construct these models to be effective, especially when we don't have a large amount of high-quality data available. It is also unclear how to maybe combine multiple sources of information. So maybe we have data from an experiment to construct a reduced model, but we also have a simplified physics model that gives us an approximate answer, and we would like to integrate it within the a bigger framework. So in this workshop, our aim will be to bring together experts from the applied math, computational science perspective that work on methods development, and they are pushing the boundaries of developing data-driven learning, and experts in plasma physics and then fusion who understand very well the application side of things and present their perspective on the usefulness of data-driven learning and the way in which this can be incorporated into multi-fidelity frameworks. And our goal is to leverage the interdisciplinary and multidisciplinary framework provided by IPAM to have these perspectives put together and also create and foster communication and collaboration between these different communities, because at the end of the day, real progress can only be made if people from different communities talk to each other. So this will be our goal in the second workshop focused on data-driven learning.
Hi, everyone. I'm Elizabeth. So this third workshop is going to be leveraging the techniques from multi-fidelity modeling in order to design devices and numerically optimize fusion reactors. So I come from the stellarator optimization community, and this is something that we think a lot about. So often when we're designing the shape of stellarator magnets, we use a low fidelity model within the optimization loop, but then as a post-processing, you perform a high fidelity optimization. And you can often improve performance by using a high fidelity model within the loop, but that becomes not practical. So we want to leverage multi-fidelity models so that we can still take advantage of higher fidelity aspects of the modeling. In addition to stellarator optimization, numerical optimization is used in designing pulses for the ICF community and designing the target shape. And in the tokamak community, numerical optimization is used for developing scenarios and optimizing the plasma shape to improve performance. So we've tried to recruit speakers from a wide range of backgrounds, from different confinement concepts, as well as the applied math community. So in addition to myself, other organizers include Lise Marie Ambert-Sherrard from the University of Arizona. She has expertise as an applied mathematician who's worked on stellarator optimization as well. Federico Felici from Google DeepMind has expertise on applying machine learning for control of tokamaks. And Orso Mangini from General Atomics has performed integrated modeling and developed frameworks for optimization of tokamaks. So as I've mentioned, we've tried to recruit speakers from a wide range of backgrounds so that we can learn from each other. So we've recruited speakers from the tokamak, stellarator, and ICF communities. We've tried to include representatives from the private fusion industry, as well as representatives from the different SIDAC groups within the US, and international participants from Europe and Asia. And we have included speakers from the applied math community who have expertise in optimization and multi-fidelity modeling. So we'd like to use this opportunity to learn from each other and apply multi-fidelity methods to device optimization.
Thank you, Emily. And Tim.
All right, good morning, everyone. I'm Tim Wildey from Sandia. It's nice to see so many familiar names and faces on the call. I'll be introducing the fourth and final workshop, on behalf of the other organizers of the workshop, Jonathan, Anna, and Christina. So the title of the fourth workshop is Multi-Fidelity Methods to Enable Robust Optimization and Real-Time Control of Fusion Processes. It's going to be May 18th through the 22nd. So what's the focus of this fourth and final workshop? So many of us believe that bringing sustainable and reliable fusion energy to reality is going to require optimizing and understanding how to really control fusion energy systems. And so, as Frank alluded to, Breakthrough at NIF was an excellent example where both high-fidelity numerical models and lower-fidelity reduced-order surrogate models played a key role in optimizing the design of the experiment that actually achieved ignition and the subsequent experiments after that. So this fourth workshop is going to bring together computational and applied mathematicians, plasma physicists, statisticians, engineers, computational scientists to get together and learn from each other and present ideas on enabling large-scale, robust optimization, optimal control, uncertainty quantification, inverse problems, optimal experimental design, and optimization under uncertainty. Of course, the emphasis is going to be on multi-fidelity methods that can help enable these capabilities. So we're looking for mathematically rigorous methods that can effectively combine experimental data, both sparse data and information-rich data, with high fidelity, but maybe computationally expensive numerical models, and as well as efficient but lower fidelity surrogate reduced order machine learning models. And so we also anticipate there'll be lots of interesting ideas presented and discussed on machine learning, emerging areas like active learning, reinforcement learning, and generative modeling. We anticipate these topics will also be discussed.
Great. Thank you very much, Tim. Great. Thank you to all the organizers who chimed in and again helped us understand the differing topics and the research communities involved within the long program. So as promised, I was going to talk a bit more about the structure of a long program and what you can expect, because some of you may not be from the mathematical sciences and might not understand what these mathematical science research institutes do. So here goes a bit of a description. So we generally have, during the long programs, during the 14 weeks, excuse me, we have 40 to 45 core participants that stay here at IPAM for the length of the program. Some more senior researchers may come and go, but for the most part, like on a given week, we have between 40 and 45 people in the building. You also have, as I mentioned before, you'll have an office space here at IPAM. IPAM has its own building on the UCLA campus. It's actually a Frank Gehry building. It's a really nice open space, welcoming environment really for collaboration. So there's boards all over the place and boards in your own offices as well and so on. And our lecture room as well it's pretty great. So this long program, it's important to note that it's not open for registration. So anyone who is interested in being at IPAM as a core participant, someone who's here for an extended period of time, needs to apply on the application page, and I'll show you that at the end, or has already been reached out to by myself. So if I've already been in communication with you, you're a more senior researcher who the organizers have deemed important to come to the workshop, and just to make sure that we have enough representation from the different areas, and that we have enough people who can mentor and help out the rest of the participants that will be here as well. What you can expect as well is, in terms of funding, is that we will contribute funds towards housing, travel, and you're also automatically registered for all of the workshops that are here during your stay. The housing, by the way, it's important to note that we have a housing coordinator that will be in contact with you exactly 4 months before the start of the long program. If you start looking for a place now, you're going to feel scared. It always works out, I promise. We've been doing this for 20-some years. So if you start looking for a place too early and reach out to people, they will not rent to you in the alley area that early before the program. So just wait for the coordinator to email you. We will not find a place for you specifically and go through the contract with you, but the coordinator is there to help facilitate this, and we'll actually post things as well. For the graduate students, in particular for international graduate students, we also have a partnership here with UCLA where they're able to offer us a couple of the UCLA graduate student housing, which is great because then we can pay for that directly ourselves and you don't have to wait for reimbursement. But for that, we would really, it's a smaller space, of course, it's for graduate student housing, but also be looking out for that. That information will come from Ginger Williams. She's our housing coordinator. So let's talk more about the format of the long program. So again, we begin the first day with orientation, this like opening day of the long program. Then the next 4 days are tutorials. As I mentioned earlier, the tutorials week is really it's lecturing. It's not research talks. We're giving lectures about the different topics that are coming up in the long program. They're really meant to be on the level of a graduate student lectures. And it's the time in which we can all hone in on a common language on a specific problem, right? So in mathematics, we might call it something. In physics, we might call it something else, and so on. So we give that time to really talk about the open problems. And then at the end of the week, we form these research groups. So it's just a way to give some structure for the next 14 weeks. So these research groups that we form at the end of the first week, we usually end up with about 12 or so at the end of the first week. And then during the long program, some of them might merge with other research groups. Some might fizzle out, and other new ones might come up. But really, it is that time in between the workshops. So you've already heard about all the workshops, but it's the time in between the workshops where all participants have mentioned that this is the most valuable time of being a core participant at IPAM. It's a time in which you're actually getting work done and where you're collaborating. The workshops are pretty busy, right? We have talks and all that, and you have maybe, some breaks here and there to talk to people. But the off workshop weeks is really where the magic happens, where you get to work and collaborate and really think, just sit in front of a board and mull over some computations, for example. So I mentioned that we've been reaching out to more senior scientists from academia or government labs and so on to provide more leadership and mentoring for the junior participants that are here. So it is our goal that everyone that is here at an IPAM Lung program feels welcome and gets something out of this program for their own career development. So the culminating workshop is at the end of the long program. So it is the 14th week. We leave on a Sunday and we go up to the UCLA Lake Arrowhead Lodge. It's an opportunity to really take stock of what has happened during the long program. And we highly recommend, in fact, every long program who's been up to Lake Arrowhead in the last 10 years, I want to say, has written a white paper that described the outlook of the long program, and it was really a forward-facing, where are we going with this community? And NSF really likes this, by the way, because it gives them an idea of what people are interested in, what is the new field, what is being worked on now. And then after the culminating workshop, so again, it ends with everybody contributing to a white paper. And by the way, I do need to mention, given that this program is in the spring, obtaining more rooms at the Lake Arrowhead Lodge can be pretty difficult. So we invite those who have been here for an extended period of time. So those who are here for the whole long program are automatically invited, because again, the idea is that we're writing this, we're giving feedback and report backs about the work done in the research groups and writing this white paper. And so it's really meant for those who've been here during the long program. And then about a year and a half after, and then 2.5 years later, we have reunions where we bring back those that were part of the long program again, to again give talks and just update each other on the work that has been done since the long program. And these have been really great as well. So the culminating workshop is always on the 14th week of a long program. So it's always on like the second week or so of December and the second week or so of June. When you are at Lake Arrowhead, you are joined by the long program that was at IPAM a year and a half ago and the long program that was at IPAM 2.5 years ago. So it's really great because you meet new people each time. There's about 80 or so of us up there. Each long program has their space where they're giving talks and so on. But then we all come together for like seminars in the evenings. And there've been really great engagements between these different research communities that have never met each other. So it's been pretty wonderful. Great. And as I promised, I would talk a bit about applying for the long program. So if you go to the webpage of the long program, MFE 2026, you'll see there's an application tab there. That application tab under the long program is for core participation for an extended time. You'll need to fill out the form, submit a CV before you even click submit. And we do have, we ask for letters of recommendation or reference letters for all, at least the name. But for junior participants, they're required. Please do send something within either your reference writer can, there's different ways that they can send it. They can email it to us directly. You can input their email address on the form, and then they'll get an email directly asking to submit through there. They can upload a PDF to that link, or they can write something brief. So we do ask that you all plan ahead and get somebody to write a reference letter for you. Finally, I do want to mention for the graduate students that are listening, if you're a graduate student that is not in a UC, we need to obtain what is called a visiting graduate research status, so VGR status. It is a process that we have to go through here within UCLA, which means that we need to do this before you can then, if you need one, apply for a visa and so on. So this needs to get done. And therefore, if you're a graduate student, please do, again, reach out to us, apply, send us an email so we can get that process started as soon as possible. Great. And if you, oh, and one other thing is, of course, if you're interested in attending only a week-long workshop, you can apply to that as well. So within the long program webpage, there's an activities tab. On that activities tab, you'll see the list of the 4 workshops that we mentioned. You can click on those links, and then each of those have their own page and their own tab for application as well. So if you're interested in just attending a workshop within the long program, you can apply to that workshop. You can also you can register directly for a workshop. It's open registration. But you could also apply for funding for attending a workshop, and funding is generally in the form of housing, and it's a very similar application. And you also have an opportunity to give a poster presentation during the workshops as well. Great. So, any questions? Yes, Michael.
Yeah, thanks for the info. If we're a workshop speaker, but maybe not able to participate in the long program, or maybe not able to attend another workshop that we're interested in, are there any remote opportunities, at least for listening in?
Oh, thank you. That's a great question. Yes, thank you for bringing that up. So we actually have a pretty great setup in our IPAM lecture room, and this was done, because of the pandemic. We have a little robot, in fact, that raises its hand if anybody on Zoom land has a question, which is really great because it alerts the in-person speaker and the audience that there's a question on Zoom. So yes, you can register for, I believe it's $10 or so registration fee to get the link for a given workshop. So definitely. As far as contributing remotely to the research groups that are formed, like for the core participation, that we don't really have infrastructure for, and again, it just doesn't work out the same. We really those that are in-house, those that are core participants, those are the ones who are really involved in the research groups that are formed. But for workshop participation, definitely you can go there now. You can go to the webpage now and register for remote participation and join the talks. We also post the talks on YouTube for those who are those speakers who sign off on allowing us to post on YouTube. I don't think we have any other questions. So thank you all again for joining. This is, as you saw when you joined the call, is being recorded. It will be posted on its own tab on the long program webpage. And we'll also send out an email when it's available. So please do encourage those in your research areas to apply, especially junior participants. Please do encourage to apply. I'll also include in the email that goes out, there is a short, like 2-minute video of one of the graduate students that was here for a long program last spring, just to kind of give you an idea from their perspective, how rewarding they found participation in a long program. So I'll include that in the email as well. But it's on our YouTube page as well if you wish to see it. Great. Well, thank you all very much. Have a wonderful day, and we'll see you all soon.
Thank you.